Welcome to our next video in the series on condensed matter theory. In this video I want to talk about Ohm's law and how to describe this within the Sommerfeld model. And what we will see is that the description actually is very similar to what we've already done in the Drude model, and therefore we can actually extend the findings and the methods that we derive here to also describe the Hall effect and the optical reflectivity, and we basically will find the same results as we had in the Drude model. So when we want to describe the conductivity of a material, we have a rod with length L, thickness A, area A where the current flows through because of a voltage. Now in quantum mechanics we want to describe this system by the Hamiltonian of the system. So to the Hamiltonian we add an electric potential. And the electric potential is such that the energy that we have is equal to E times the voltage, which is position dependent, and drops from V to 0 when we put on a voltage V in your system, or E times phi as a function of R instead of V. And the electrical field that belongs to this potential is the gradient of phi. The Hamiltonian then becomes the kinetic energy that we have, h bar squared k squared over 2m times the number operator that counts how much electrons we have with that momentum, plus the interaction with the potential, the electric potential. Now if you want to calculate the ground state and eigenstates of this Hamiltonian, then placing your electron at minus infinite will generate an infinite energy for your electric potential, and therefore the ground state of this Hamiltonian would be to shift all electrons to minus infinite. So this is not an electron that we want to look at the stationary states for. Now what we do in the experiment is also not a stationary situation. We have our solid, which is near to its ground state, then we add a potential and electrons start to move. So we definitely do not want to look at the stationary solutions of this Hamiltonian. In order to describe the experiment, we can start from H0, which is the Hamiltonian of the Sommerfeld model, and includes the kinetic energy of the Hamiltonians without the additional potential or the electrical voltage. And we can see how ground states of this Hamiltonian start to move in time when we add H1 to it, which is minus E0 dot R for our case, a constant potential over a distance L. Well, the ground state of H0 is the wave function that we take at time equals 0. And we know this, we've seen this before. These are the one particle eigenstates filled up to the Fermi wave vector. So we create all particles with a wave vector smaller than the Fermi wave vector for both spin up as well as spin down out of the vacuum. And the one particle basis functions are given by 1 over V e to the I k dot r, where we've confined our one particle wave functions to a box of volume V, and of course in the end we'll take the limit of that volume to infinite. We now want to know how our wave functions will evolve in time by the full Hamiltonian h. Well, we can formally write this down, and we will focus first on the behavior of a single electron and then extend this to the behavior of many electrons. And the time evolution is e to the minus I h0 plus h1 t over h bar, and then the wave function at t equals 0. Is e to the minus I h0 plus h1 t over h bar square root 1 over v e to the I k dot r. Well, the time evolution for either h0 or h1 is actually simple to calculate. E to the minus I h0 t over h bar square root 1 over v e to the I k dot r. These are eigenstates of that Hamiltonian. So they are stationary states. The state stays the same. We do get an additional phase, and the phase is just given by the energy of that system, which is e to the I h bar squared k squared over 2m times t divided by h bar, so the square there drops, and then the original function that we had, e to the I k dot r. So when we evolve with h0, we just gain an additional phase. Now if we do the time evolution with h1, t over h bar square root 1 over v e to the I k dot r, then we have to look at the Hamiltonian, and we get an additional factor e to the minus I e a0 t over h bar. So our wave function becomes square root 1 over v e to the I k dot r for the original state, and then the h1 is giving you a minus e0 divided by h bar times t dot r. So the propagation with h0 gives you an additional phase. The propagation with h1 shifts the k vector. Now the propagation with both Hamiltonians simultaneously is more problematic than one might think from these simple behaviors, because the commutator of these two operators is non-zero. So we cannot say that the propagation of both simultaneously is not the propagation with one Hamiltonian and then the propagation with the other Hamiltonian. Now there is a solution. We can actually use a reasonable standard solution. If the time over which we evolve is really small, basically going to the limit to 0, then the commutators become, or the higher order operators become smaller and smaller, or less and less important, and we can make this factorization. So we can write our exponent as a time evolution over a small time. We divide by n and we let n go to infinite. And then of course you have to make this time evolution n times. So we sum j is 1 to n. So instead of a time evolution by time t, I make a time evolution of time t over n and repeat this n times. Now my exponent here is small, so I can factorize them. And this is limit n going to infinite pi j is 1 to n e to the minus I h0 t over n h bar e to the minus I h1 t over n h bar. Now let's have a look what this time evolution operator does to my wave function. If I evolve with h1 for a time t over n h bar, I will shift my k vector by an e0 h bar t over n. So that's a small shift of your k vector. Then I evolve with h0. We don't have the original function at e to the I k dot r, but we now have k minus some shift. That is, however, still an eigenstate of h0. So this propagation will just give me some additional phase. Then I propagate with h1 again. h1, it doesn't matter what the k vector is with which I start, so that gives me a shift. Then I propagate with h0, that gives me a phase, a shift, a phase, a shift, a phase. Then I have to make the product of all of them. We have to remember that each time you apply h0, the phase that you get is different. So in the end, the phase shift that we get is not the original phase shift, but some involved quantity. But that's just the phase of the wave function. It will drop out of every expectation value I take. So here I have some phase. And then we have the wave function shifted in the momentum that we had before by e to the e0 over h bar times t over n times n dot r. And here we can say this is delta k, which is equal to minus e0 over h bar times t. Now this is the behavior of a single electron. A single electron is getting accelerated such that its k vector, its momentum, changes with minus e0 over h bar times t. Now let's have a look at the many electron wave function. Well, each electron is shifted by a wave vector delta k due to the time evolution. That is the same wave vector for all electrons. So the Pauli principle that says that one electron cannot be occupied in the same, or two electrons cannot occupy the same state, will be still adhered to even when you shift all electrons by the same amount of momentum. So we have some phase that we gain, which is the product of the phase that we gain, which is some phase for each k vector. Then we have the product of all k vectors smaller than the Fermi vector, and we generate our wave function at k plus delta k. For spin up, we could generate an electron at k plus delta k. For spin down, out of the vacuum, and delta k is minus e0 over h bar times t. Now with this we can look at the average k vector that we have when we include scattering. Without any scattering mechanism, the electrons would accelerate and keep on accelerating until they become faster than the speed of light, which of course then at least tells you there is something wrong. What we do is just like the Drude model, we add some scattering. At some point in time, that electron that accelerates will scatter, and at that point it's back to its original velocity. So if we now do the average over this state, we will get a minus e over h bar times tau. Where the scattering in the Drude model could be thought of as you scatter from the atoms. The scattering mechanism here becomes even more unclear. And we'll talk about this a bit later to really show that we can talk about scattering length, and at the moment it's really unclear why and how you scatter. Just based on the arguments that we've seen in the Drude model, you should expect that at some point in time there's an average time that this electron can accelerate before it scatters, and then it starts over again, or that acceleration can be turned around. You come, you accelerate, then you scatter, then you move in all different directions. So there is a maximum time that you can freely accelerate, and that maximum time is exactly our scattering time tau. Well, we're now already back to the results we had. In the Drude model, we can calculate the velocity as h bar k over m. So the average velocity is minus e tau e over m. With that we can calculate the current, and e squared tau e over m. And the conductivity, which is just a prefactor here, which is ne squared tau over m. And this, of course, are the results that we had in the Drude model. So although we treat our electrons quantum mechanically, an electrical field still accelerates the electrons in the same way, and everything else from the Drude model follows, except that of course our scattering mechanism is getting more and more unclear what it really is. So let's have a look at some physical meaning of what is going on here. For that we can have a look at our Fermi surface. So in k-space, kx, ky, kz, we have our Fermi sphere. Given by the length of the wave vector is the Fermi wave vector. And the states inside the Fermi sphere are occupied. So this is the picture that you have without an external electrical field. Now we turn on an electrical field, and let's put this in the y direction. Then all electrons start to accelerate, they shift with k vector, at some point they scatter, and what we find is that you get a shift of delta k, and around this you now have your new sphere, which is no longer centered around the position k is equal to 0, but is centered around the position delta k. Now you can think of an electron, it is accelerated, therefore it's shifting in k space. Then at some point it sits here, it hits an atom, it scatters, and it scatters back to this point in k space. And then it can be accelerated again. So if you follow individual electrons, which of course for identical particles is slightly problematic, but then you would say that the electron is accelerated until it hits the boundary of the Fermi sphere, and that velocity then is scattered back. And in that sense the electrons move along. That is a cartoon-like picture that you have when you still want to follow a single electron in quantum mechanics. Now let's have a look what is the physical origin of your scattering time. So electrons accelerate for a certain time and then they scatter. And Drude assumed that this is because you have your nuclei and you scatter from those nuclei. And an electron should have a very strong interaction with the nuclei, that's the Coulomb force. So we can put in some numbers and see what comes out. And instead of looking at scattering times, we can look at scattering lengths. We can look how much does an electron travel in this time. And an electron that scatters is an electron that sits at the Fermi surface. So we take the time and we multiply it with the Fermi velocity to get a typical distance of these electrons. And the Fermi velocity is h bar kF divided by m. If you look at copper at 4 Kelvin, then the scattering time, which you can measure with conductivity and Hall effect measurements, is something like 10 to the minus 8 seconds. If you then put in the Fermi velocity, which you can calculate because you know the electron density in your system, and you know your Brillouin zone size, you know the atom distances, you get that the scattering length is about 1 centimeter. That means you travel about 5 times 10 to the 7 atoms before you scatter. So this electron travels past 10 to the 7 atoms before it scatters. So the scattering is really not the electrostatic potential of the atoms that sit on a regular lattice. It must be something else. And later in this lecture we will have a look at this and we will show first of all that when the electrons sit on a perfect regular lattice, then indeed the quasi-particle that emerges for the electron, or the wave package that emerges for the electron, does not scatter off that lattice anymore. And furthermore, we will see even later that when we put in this order, we can get a scattering time, which then is the minus the imaginary part of the self-energy of the Green's function that determines the propagation of the electrons. But that later in the lecture. So far we have shown that we can explain Ohm's law within the Sommerfeld model, and with a very similar kind of derivation you can explain also the Hall effect or the DC and AC conductivities of the material. Thank you very much. See you in the next video. Stay healthy.